My name is Mike Moore, and this is the Frass Meteorite. I call it the Frass Meteorite because it landed on my great-aunt's ranch, and her name was Frass. Her ranch is near Canadian, Texas, and this appeared in the pasture one day. It happened, I believe, in the winter of 70-71, if my memory serves me correct. We were feeding cattle that winter, making every pasture every day. We'd made this particular pasture every day the entire winter, and there hadn't been any rocks at all in it. There's no rocks anywhere on the ranch. This particular day, we drove into what we call the North Meadow. The second we turned north, we both saw this rock sitting on the surface more than a half a mile away. In the wintertime, the grass is yellow and short, and this red rock just stood out like a sore thumb. My aunt exclaimed, "What is that?" And my first thought is it had to be a meteorite, since it apparently had fallen from the sky. So I named it the Frass Meteorite because it landed on the Frass Ranch. As far as the evidence of its Martian origin goes, there's a number of things that I would like to discuss. The fusion crust is the main area of contention on the meteorite. Most meteorites are very dense and heavy material. As they come through the atmosphere, they exhibit characteristic melting and burning around the rock. The Frass meteorite is different than the typical meteorite since it was apparently made on a smaller planet with lower gravity. Therefore, it's a very lightweight rock, and it also has very, very thin walls. So the fusion crust on this rock is different than that of a typical meteorite. There are several ways to view the fusion crust. Macroscopically, you can see it over the entire meteorite. This section all in here, you can see, is very grossly melted. This would have been the bottom of the meteorite coming through the atmosphere. The reason I believe it was the bottom is because it had the older material on it, which appears to be denser than the younger material. So it acted like a kind of a weight on a paper airplane to hold this on the bottom. Also, the rock has a shape much like some of the lifting bodies that NASA used to test in the 60s. There's kind of a triangular shape, and this would have been the head of it, and this would have been basically the bottom of it as it was flying through the atmosphere. So since it had a single orientation, just as a space shuttle has a single orientation, the heating is different on it and the melting is different depending if it was on the bottom or the top. There's much more melting from this line around down than there is on top, and parts of the back of it show very little melting because they would have been in a position that was with little air flowing. So you can see here that there's gross melting occurred. There's also another section here where gross melting occurred that you can see with an unaided eye without using a microscope. Now, most of the fusion crust is better seen through the microscope because the rock is really composed of just millions of fine little walls. Each wall of this meteorite is about the thickness of a piece of paper. So if you look at it under a microscope, what you see is that the outer edges, whatever is sticking out, is the most melted, and then the further it goes down into the vesicle, the less melting that you see. But we have a number of pictures that I've taken of massive amounts of melting that occurred, and you can see melting over every spot of the meteorite. If you look through the microscope, you can see the fusion crust everywhere on it. I may think of other things to say later about the fusion crust, but then I'll come back to it if I do. The next thing I'd like to discuss is the elemental oxides. All of geology is built around taking these elemental oxides and trying to determine what it's telling us about something. When the Pathfinder was on Mars, it took some measurements of the Martian chemistry. Also, the early Viking had taken some measurements, and then we have a number of other Martian meteorites, so we have actually taken the measurement, the chemistry of the meteorites. I had Chemex Labs do all of the elemental oxides, and that's these reports here and here. And then what I've done is plotted them. Every one has been normalized. What that means is you take the element that you're looking at and divide it by the silicon content. You do that on both and then plot the resulting numbers. there's several interesting features about the elemental oxide that I think clearly show Martian. First of all, two of the samples that I took, that I labeled Sand 2 and Sand 3, by all accounts fall in Martian territory as compared to the other measurements from Viking, Pathfinder, and other meteorites. Some of the measurements fall outside of those ranges of the rock itself. But the interesting point is that they all came from the rock, so they all must be considered at the same time. And when I plot every graph, no matter which one it is, I get a linear nature of the meteorite and all of its contents. It's 5 different samples here, and they always show this linear nature. And what that tells us from classical geology is that all these materials were made at the same volcano. Typically, what would happen on Earth is a volcano would be intermixed with other material, and then that causes a straight line to be a curved line. Even on Earth, it's considered, though, if you get a straight line from the lava and different contents, if it's a straight line, it means that it came from the same volcano. The difference here, though, is that we have material representing millions and millions of years that came from the same volcano. Apparently, that was stable and isolated for a great long period of time. Mars is the one planet we know that has the largest and oldest volcanoes in the solar system. We now think the volcanoes on Mars are about 3.5 billion years old. They've been in the same location and active, apparently, for that period of time. This rock appears by the elemental oxides to be the end result of that process. If we look at the surface of Mars, originally when the volcanoes started, they laid down a large sheet and then continued to build the material to make the volcano. What happens as volcanoes die, too, is that the venting moves from the main caldera and becomes what we call side venting, where it comes out the side of the volcano. I think my rock shows to be a side vent because the ages of the rock and the chemistry seem to show that. The chemistry shows these rocks to be very, very old with little reworking in a volcanic system. And interesting enough, the youngest age of material in the meteorite has the oldest chemistry. And I think that clearly shows side venting, because what it means is that this material was laid down by the volcano in the early days, set on the surface of the planet for millions, maybe billions of years, and was unaffected. And then as the side venting occurred, that material was remelted one more time, allowing it to be the oldest appearing material with the youngest date. So the linear nature of the chemistry, the fact that several of the samples test Martian by all accounts, the fact that the youngest rock has the oldest chemistry, I think are all clear indications of another planet besides Earth. There was actually 36 million years between these two lava flows, and if you interpolate that, you would have hundreds of millions of years shown in the whole process here. The next thing I'd like to discuss is the ages of the material. When I first started trying to determine the age, of course I didn't know if there was one age or more than one age. I knew that every time that I'd taken a sample, there was lots of little pieces of volcanic material in there, and I didn't know if those pieces were inside the meteorite to start with, or they had occurred when I took the sample and I broke it apart. So when the first sample that I took to send in for an age came from the underside of the meteorite, and it was taken from this location right here. All Martian meteorites found to date, besides this one, have been very old, the youngest being maybe 150 or 200 million years old, and some of them being as old as 4 billion years. So I was expecting an old date on this when I had it dated. When I sent the material off to Geochron Labs, he called me back and he said that they had done half of the test and they could determine that this couldn't be more than a few tens of millions of years old. And so we were worried that since this sample had come from the outside, that it may be that the fusion crust, the melting of coming to the atmosphere, might have reset those clocks. So in order to get a more accurate sample, I took a core sample, and what I did was I took a piece of half-inch copper tubing, and I literally just drove it into the rock. It goes in about 8 or 10 inches. There's a hole here, and we'll show that later. I pulled that sample out. Here's a picture of the experiment right here. Here's the copper tube. Here's the core samples that came out of it. And then here's a number of other things. There was quite a bit of sand that came out. Each of the vesicles in the rock is full of this sand, and so I captured it all in a petri dish. At that point, I also wondered about what was going on. As I told you, I've wondered for a long time if the little particles came inside the meteorite or were they all made from the meteorite when I took the samples. Here's one thing that I discovered, though, is when I put water on these 3 little clods, I would call them, that came out of the larger vesicles. It was just a clod of dirt, looked like that. When I put water on it, I discovered that there was a rock inside of it. Logically, that told me that this rock had to be older than the other rock because it was inside the other rock. So at that point, it took me several weeks to learn to recognize these. I gathered up a number of these pieces that I finally was able to distinguish by 2 different characteristics. The older rock is redder in color, and it has much smaller vesicles. The younger rock is grayer in color and has much enlarged vesicles. So at that point, I sent in this sample of the I sent in one of these to be tested, which is a core sample of the younger, the gray material. It came back at 13 million years old. I also sent in this sample, these what he called picked grains, a number of these little pieces that I'd found. They came back at 49 million years old. But I'd still taken this first sample right here, and I had him finish the test on it, and it came back at 29 million years old. Then when I went back and looked, I realized that this sample here was a mixture of the 2 different kinds of materials, and so it really acted as a control, the 29 million years being between the 13 and 49, indicating that all 3 dates are probably correct. Now, what I'd like to discuss next is the boundary layer and the butterscotch colored sand. From my observations of the meteorite, it appears to me that it's laid on the surface its entire existence. What we have first is a red rock, which is right here, and which is all across the bottom, which is we're seeing right here. You can see the red color. It appeared to be a layer about 1/4 of an inch thick that was laying on the surface that occurred at 49 million years ago, and then it got melted and picked up to the other rock when it flowed at 13 million years ago. So there's about 1/4 of an inch layer across the bottom of it, of the older material, and then the younger material starts, and all of that is separated by this boundary layer. As you can see, a number of spots I've broken through the boundary layer and looked, and in no place have I found this boundary layer to be more than about 1/16 of an inch thick. The separation between 49 million years ago and 13 million years ago, apparently only this much dust blew in that 36 million years. To me, that's very indicative of Mars. We have good reason to believe that it's been dry during that period. Mars has this butterscotch colored sand, and it's found all through the meteorite. You can see it everywhere that the meteorite is broken open, and even across the top of it here, there's a number of places where this butterscotch colored sand sticks through. And by the way, if you look at it under the microscope, you'll see that the sand is melted as part of the fusion crust. A lot of the scientists think that fusion crust has to be black, but the fusion crust is formed by the material itself melting when it goes through the atmosphere. So there's places on here I have yellow fusion crust or butterscotch colored. I have places that it's red, places it's gray, there's places it is black, and there's places that it's even purple. I don't know what material was there, but there's some very beautiful purple fusion crust on the meteorite. So this boundary layer, I think, is clear indication of Martian origin. The next thing is magnetic dust. When I took these core samples, I wondered if there was magnetic dust in the meteorite, because we know there's magnetic dust on Mars. So what I did was I took a magnet, and I didn't touch any of this material. I just ran it across the top of it while watching through my microscope. I saw quite a number of particles jump up and attach themselves to the magnet, and they're all shown there in this picture. And of course, this experiment or any other experiment I've done can be reproduced to see if the results are the same. We can get another sample of material from the inside of the meteorite, and we can see if it has magnetic dust. Only one place on the planet Earth has magnetic dust. That's in Africa, I haven't been to Africa, and neither has the meteorite. It's much more likely to accumulate that magnetic dust on Mars. The next thing is the glass ingots. Here's a picture of one right here. Among the meteorite experts and the different geologists that have seen this, there's two sets of opinions have come. The first one say that it is melted all over for sure, and they call it a volcanic bomb. Logically, that can't be correct because a volcanic bomb cannot have two different dates of creation. A volcanic bomb is something that's shot out of a volcano in one action. So it cannot have two separate dates of creation and be a volcanic bomb. The other group say it's not melted at all, which to me is very obvious that it is melted, that all of these actions are the result of desert varnish, which is the actions of bacteria and weather that occur on a rock as it sits in the desert for hundreds or thousands of years. Now, my evidence of finding this shows that it only sat on the surface of our planet the one night that I found it. So it didn't sit in any desert for hundreds of thousands of years. In fact, I think I can show that the majority of the rock hasn't been wet for at least 13 million years, and that just the application of little bits of water causes the rock to fall apart. So as part of the further evidence that this did go through an entry into the atmosphere and did go through the heating that's necessary, what I found in a number of the outer vesicles, I found 3 or 4 of them so far, are little glass ingots, where apparently the sand that was in that vesicle melted during the heat of high re-entry, and then it cooled into a little glass-shaped little glass ingot, like a little paperweight. It's actually got the little particles in it that didn't melt, and so the exact temperature that went to could be determined if someone would just do a melting point on the glass and a melting point on the particles that didn't melt. I think we could know exactly how hot it got, but sand generally melts at about 2,000 degrees, so I think I have evidence that the outside of the rock got to at least 2,000 degrees. Other evidence of Martian origin. Okay, we're going to take a break and we'll be back in a few minutes. We're back now, and we're going to talk about the structure and composition of the meteorite. This picture here shows basically the structure throughout the entire meteorite. It appears to be the majority of it was made 13 million years ago on the surface of Mars when there was very little atmosphere and probably no ocean. The older rock appears to be made when the atmospheric conditions were more dense and maybe an ocean was still present. I think that accounts for the difference in the size of the vesicles. And so what we see in most of it, if you can imagine this lava oozing on Mars with very little atmospheric pressure to hold it back, it's going to be very frothy, going to make very thin walls, and it's going to make large vesicles, and that's basically what we see. Also, the surface of Mars would have been very cool, so it would have cooled very quickly. We also see that in the thin sections when we look at it. There are no inclusions in this rock, which indicates that it cooled very, very rapidly. The shape of it is much like pillow lava on Earth, which cools rapidly because it forms under the ocean, and the ocean water cools it, given the round shape. And this is what's called a parting plane right here, where the lava separates from the main flow. I think all those conditions happened on Mars, but it was the cold conditions on the surface, not water, that caused it to have that shape. Also, from the core samples, when we look at the structure and composition, this is a piece from the core of it. It's taken at this location here, and it was taken by driving a piece of copper tubing into the rock. Now, if you've ever dealt with earth rocks, you'd see that you'd have a whole lot of trouble driving copper tubing into a rock. The rock is just so delicate, though, and these walls are all so thin that I was able to do that. Then I pulled this out at that point, removed these from it, and that's where I got the core samples. Every bit of the interior of it is so delicate that you can actually break it with your fingernail. All of these, I believe, are indications of its creation on a planet that's smaller and has less atmospheric pressure than Earth. The rock is very light too. It weighs only 22 pounds for the entire rock. The next thing that I did too, and we've pretty much discussed the core sample, the next thing I did too was several water experiments, because I reasoned that if the rock had been on Mars, that it probably wouldn't have been wet for quite some time. And so I've done a number of things where I've put small amounts of water on the material. Even on the outside of the rock, putting a single drop causes it to come apart. Apparently all the bonds that's holding it together are partly the ones from the lava being hot and sticking to things, but a lot of the other bonds are made at whatever point that the water did evaporate from it, and so they're very, very weak bonds. If you put a drop of water, it rehydrates that, and these pieces just fall off. And also this experiment over here, I think, clearly shows that this piece was in water at one time, this older piece at 49 million years old. This looks like to me that it came from a dry bed of sand. At one point it was laying on the surface, got wet, got trapped in here, then got dry, and then got trapped in the meteorite. So that's what we're looking at. The next thing that I'd like to discuss is some of the living things that we found in the meteorite and how I believe they're indicative of life on Mars. On this side, we'll show you the close-up in a minute, there's a small clamshell right here. It appears to be an ocean creature. Other creatures we found in it include this radial symmetry creature, which looks much like a radial symmetry Earth-ocean creature. Also in the rock, we found quite a number of worm-type things. We found things that look like bugs. It appears to me they all have 8 legs. This particular object here looks much like an ocean creature, maybe a shrimp of some type. But what's interesting is that nothing I've found so far appears to have any eyes or really any kind of face. Everything appears to be very simple and much like we'd find in a cave creature on Earth. What I suspect is that there was never enough light on Mars for eyes to actually develop, at least in the creatures that I've seen. But on the other hand, we do have several structures that look like trees. This piece here looks like the piece of the outer layer of some kind of a tree, although it's very, very tiny. The trees on Mars might not have been any bigger than this, and if there wasn't visible light getting to the surface, it makes me wonder what the trees were using. Apparently they'd be using some other wavelength of light, and so would probably have different mechanisms than we have on Earth. This appears to be a little piece of a tree trunk. It has a definite inner and outer layers, and it has a place where it appears a little branch had come off. All of these have come from inside the meteorite. All of these apparently would then have to be at least 13 million years old, because that's the date of the material, and yet many of these are right next to the pieces of 49 million year old lava. So some of these creatures could well be as old as the dinosaurs, including this one here that appears to have been in the water and gotten torn up. So this creature could be as old as the dinosaur, yet none of these are preserved by fossilization or any other method. It's the actual little bodies of the creatures, which I think would make it the oldest unfossilized living things on the planet. On Earth, things just can't stick around for 13 million years without being fossilized or something happening to them. These have all been perfectly preserved, and we think there was little water on Mars during this time. There's little water in space, so it makes a lot of sense that these would be preserved that amount of time coming from Mars. It doesn't make sense that they'd be preserved coming from Earth. This material here, I don't know what it is, but it appears to be newly formed in the meteorite, and it's either some type of living thing or it may be some type of food that they're actually producing and storing. And then what's most interesting about the meteorite to me, and we'll show through the microscope, is the number of little filament creatures. I've called these a glassy Martian rock fungus. They remind me of a fungus on Earth because they have little filaments growing everywhere. These are very slow growing though, and I've now documented them growing in the meteorite for 30 years without light or liquid water. And when I took the core sample and I removed the innermost core, I found these things growing inside the meteorite. And they have a number of interesting characteristics too. They always have pieces of sand on the outside of them, and if you look in the older colonies, you see where they're bringing the sand together for some purpose, I don't know what. In other places, they appear to be manufacturing some type of glass material. There's large structures, well, large under the microscope, structures that they appear to have built. I would assume they're either storing their food or water or something that has to do with their life cycle. But they grow very, very slowly. They do like earth creatures. In the meteorite, I find them typically around the insect bodies and other organic material in the meteorite. I suspect they may have acted much like a living spider web in their day. As these insect species would come along, they would get caught up and stuck in these little systems, and then they would eat them. And we'll show you the close-up also of these creatures that I've taken from the meteorite, put in this dish, and then fed them an earthly fly. And you can see clearly that they're attached to it now, and they're apparently consuming its organics. When I first found the meteorite, all of it was wiped clean from coming through the atmosphere, and none of these things were visible. It was approximately 15 years ago that I noticed the first ones coming out of this crevice here, and I thought that rather strange, but there was no other evidence of life on Mars, and so I just kind of put it in the back of my mind. I didn't really think about it seriously until 1996 when NASA announced that they'd found possible life in one of their Martian meteorites. And that's when I began to study it, and I've now documented them growing in petri dishes and in the meteorite for all of this time. They grow very slowly, but virtually every vesicle on the upper side of this rock has these things growing in it and coming out of it. And the characteristics of this life, to me, indicate something that would evolve on Mars. They have apparently done it with learned to live with very little water and very little light. And I suspect what they've done is incorporated silicon in their diet, much like earth creatures incorporate calcium or something to build a home. Silicon is the perfect material if you don't want to lose water. We use it ourselves to make our own glasses and containers, and it appears that's what they've done. And as you see through the microscopic views, they come in a number of colors. Most of them are kind of a clear color, but there's some very bright colored ones, bronze. There's some red colors. Blue is very common. Black and brown are present. Orange, I found. And even a few green ones. So we can now say for sure there are green Martians. Okay, I think we'll take another break on that. I'd like to finish up by summarizing the evidence again and then showing you what tests that I would like to have performed. And in my opinion, this rock appears to be from Mars. It appears to be one of the last rocks made on Mars. I have the experience of finding this on my aunt's ranch. I know for certain in my own experiences that it was never there before. I'm very familiar with the ranch. I took a lot of time whenever I did find it, carefully examining the whole area around it, and there was no signs of any kind of footprints or any disturbances whatsoever other than a small indentation about 18 inches away. Looked like to me that it made one hop. It also looked like to me that it came from the north. I don't know if that's significant or not. The rock is covered with a fusion crust. Everywhere on it you can see the melting that occurred when it came to the atmosphere. The melting occurred after the different rocks was laid down and after the sand was in the rock. The two different ages of material separated by 36 million years. It's just something that doesn't happen on Earth. That seems very indicative of Mars. The little glass structures, all the other evidence of heating is all important. The elemental oxides clearly show a linear nature in every graph. And what that means is apparently the rock and all of its contents were made by the same volcano without being mixed by material from other volcanoes. Also, we've taken core samples. We know the rock to be very, very delicate. It's very light in weight. It only weighs 22 pounds. An earth rock of this size would typically weigh 50 or 100 pounds. and a typical meteorite of this size would weigh 300 pounds. So it clearly shows to have been created on a planet with a smaller gravity to me. The sandy material in it is unlike the sand that's found at the landing site. It's much simpler, and it's full of all of this volcanic material. At the landing site, the sand is more complex, but there's no lava-type material in it whatsoever. The two different ages of the material are very easy to distinguish by light and by the density of them. So all of these add together, I think, to clearly show that the rock didn't come from Earth, and that I've gained enough evidence that further testing should be done to determine the truth of this matter. Now, as far as further testing, what I would like done is we need more comprehensive elemental oxides. We need them taken of just the rock, the two different ages of the rock itself, and many of the inclusions in it. All of the testing I've done has been done by sending samples to Chemex Lab, which requires me to send them more than a gram of material, which is then vaporized and wasted in the sample. But since the rock was made by lava moving through a bed of sand, then every surface of this is covered with a fine layer of that sand. So when I send this in, I'm not getting the exact elemental oxides of the rock, I'm getting the rock and the sand together. And we need to get exactly of the rock and the different things in it to get the exact elemental oxides. Also, I would like to have these organic materials that I'm finding in here dated. If I'm right on the potassium argon date of the main rock at 13 million years, then anything that we find inside that must be more than 13 million years old. It seems like to me some simple testing of that organic material could determine if it's that old or not. If it is, that would lead, that'd be more evidence of Martian origin. I'd like to have the DNA of the little living creatures in here taken. If it is from Mars, first of all, we don't even know if it is organic. I'm assuming it is. We don't know that if it would have DNA. I'm assuming that it does. But that's something that needs to be done. That could be done very easily and inexpensively, and we could compare it to DNA of known species on Earth. Again, if it showed to be a DNA not known on Earth, then that would be more evidence that it comes from somewhere else. Density measurements of the rock is another experiment I would like to have done. I've tried to get people to do it. I could do some primitive ones, but I would have to take large samples, and I would have to put them in water. And I don't want to put them in water because I think that would destroy part of the evidence. So what I need is somebody with very accurate scales and that can measure small displacements of water so that we could do the density of the rock, the gray rock and the red rock. And then I would like to remelt both of them under Earth's gravity and do the density again. I think the evidence is strong. This was on the surface of its planet of origin and has never been below the surface. I found no material in it that appears to have been below the surface. Everything on the rock and all of its contents appear to be surface material. So some density experiments, I think, would lend more evidence of where it came from. Also, I would love to have an electron microscope done of the rock and all of its contents. There's a lot of them, all these little insect bodies and stuff, and there's lots of things in here that I just can't get proper photographs of. Even the little glassy creatures. I think it'd be very interesting to do some electron microscope work of them and see if we can see what they're like inside. They appear to have a channel inside of them where they transport material, but we don't know that until we do some kind of studies. I'd also like to have a melting point test done. One of my claims is this rock is made much like a space shuttle heat tile. It's made of very thin walls with lots of vesicles, and the walls are very, very high in silicon. I've taken a piece of this and heated it to 1,000 degrees, and 5 minutes later you can hold it in your hand. It's perfectly room temperature. So I think some melting point tests would bolster my claim that this rock came through the atmosphere and it just had particular characteristics that allowed it to withstand the heating better than most meteorites. The heating is clearly visible all over the rock, but it's made of a material that withstands that heat and dissipates it very quickly. I suspect the interior of the rock never got hot during its entry into the Earth's atmosphere, and it appears to me the entire rock was cool by the time it hit the ground because these little glass ingots are perfectly formed. If they had still been wet when they hit the ground, they would be in little droplets rather than in solid glass ingots. On the bottom, they all appear to be shaped like the vesicle, and then they're flat on top. And those came right out of these little vesicles in the rock, and we'll show those. There's other tests that could be done. two tests that NASA used to determine Martian origin is oxygen isotope ratio. It appears that certain isotopes of oxygen are a little more predominant on Mars than they are on Earth, and if we could do those tests, that would lead more evidence for or against its Martian origin. The other thing that NASA uses is atmospheric gases. Since we have been on Mars and since we have measured the atmospheric composition, NASA has measured very similar compositions in the meteorites they found that they claim were from Mars, and so that would be another obvious test to be done on this meteorite to see if its atmospheric gases are similar to those that we find on Mars. So that's the test that I would like to have done. I think that I've done enough work and presented enough evidence here to show that this rock needs to be studied further. I've exhausted all of my resources and all of my abilities to continue this testing. I need help from other people that's willing to look at it and help me determine the truth of it. Something like this is way too important for somebody just to say, no, we shouldn't test it any further. The conflict that I've got into is I've challenged the whole meteorite community on this, and basically their whole statement has been this: in their opinion, this rock is not a meteorite, and no further testing should be done to see if their opinion is right or to see if my evidence is right. And I think this is a lot closer to being evidence than the expert opinion, when I'm claiming that no expert has ever seen a meteorite like this, so how could there be an expert on meteorites that they've never seen before? And we obviously know these rocks exist. We see them in every picture of Mars that we look at. Gray rocks, many of them rounded, many of them with a crevice, and many of them with a red streak on it. Well, my rock explains why there would be the red streaks on it. The same mechanism would have been working. My rock, I think, explains why there's a crevice on those rocks and why there's a rounded shape. Part of the rounding shape comes from the fact that the rock is so delicate and made of so many fine little thin walls. Any movement at all of the rock tends to break off any little walls that are sticking out, and so the rock would just naturally tend towards a rounded shape. Also, the latest evidence from the Mir reentry and from other satellite reentries is that a rounded object has a much greater chance of making it through the atmosphere with little or no damage. The evidence is we have quite a number of fuel tanks from depleted spaceships that have made the trip to Earth and are virtually unharmed. They're in museums around the world. One of them landed in Texas, and I saw it on a video just a week or so ago. And I think that's part of the reason that helped this rock get through the atmosphere. So what we need is help on this to determine the truth of the matter. I'm willing to take any kind of lie detector or any kind of test to determine my own integrity, and if what I'm telling you is the truth about this, and I'm willing to allow any part of the rock to be tested to repeat or do the additional test so that we know the truth. Nothing is being hidden here, and nothing is kept from anybody that wants to determine the truth. All I've asked is that we do additional tests and try to determine it. And that's the reason that we're making this video, is to try to get help in determining the origin of the Frass Meteorite. Oh yeah, and if you want to contact me, my website is, I have two main websites, www.micromike.com, M-I-C-R-O-M-I-K-E, and the other one is www.marslife.com, M-A-R-S-L-I-F-E. You can write to me. If you want to contact me, my email address is mike@micromike.com. And we thank you for your time and attention in looking into this matter. it's what allows us to understand what it means. Not
Yeah.
you're not recording sound or anything.
No, actually it is recording sound, but I took your lavalier mic off. It's just getting ambient room sound. The purpose of this is not for the sound. The purpose is more for me, so I can have this stuff.
Yeah, and you may want to get this little quote from Dr. Treatman too. I don't know if we can work that in, but see, he said on that graph, analysis of Frass sand do plot in the area of Mars rocks, but one cannot conclude that the sand is from Mars. The Mars and Earth areas of this graph are not applicable to sand, only basalt lava rocks or their close relatives. Well, what I've shown, if he listened, was that the rock and all of its contents are basalt derivatives from the same volcano. And so they do apply, and those measurements are valid. Well, you know, I imagine somebody put some of this in Excel, but it didn't seem any good for me to do it over again. I need to find somebody else to...
Move your finger up and down that and point out that one spot again. Point it out there.
You want me to talk?
Yeah, just because that'll remind me what it was.
Yeah, we'll see what Dr. Treatman is claiming that we couldn't call these sand 2 and sand 3 as Martian because they may not be basalt derivatives. But what he doesn't understand is the sand 1 sample, I mechanically isolated everything that wasn't clearly a basalt, all the very finer particles, and had them tested separately, and they're still linear. So that means that these particles came from the same material that the basic source material came from. The very finest particles in it came from the same volcano that made the overall rock.
Okay. Now you talked about each one of these.
Age has the oldest chemistry. You see, this line here really represents the progression of these materials. As we talked, if things cool very quickly and don't have time for things to precipitate out in them, that's what we're seeing with this chemistry here. But then over time, if it's been in the volcano for a very long period of time...
Just go ahead.
This represents several important things about the meteorite. First of all, the core sample. One of the things I wanted to demonstrate was how delicate the meteorite is. I was able to... this was the core sample experiment, and it shows several things. First of all, I wanted to show how delicate the rock is by being able to drive a half-inch piece of copper tubing into it. Everybody knows how weak copper is, and so it gives everybody an understanding of how delicate the rock is. The core samples clearly show the internal structure of it, resulting in a number of little pieces of material, including other little rocks that came out of it. Clearly showed magnetic material inside the meteorite, and clearly showed that some of the other rocks were inside the meteorite too, which is the first indication I had that there was more than one age to it. Over here we have clear indication of the different types of rock. The older rock, 49 million years old, smaller vesicles, has been wet, but not wet much because it still has very sharp edges on it. So it was in some water, but it was never tumbled enough to remove the sharp edges. The younger rock at 13 million years old appears never to have been wet, and the contents appear never to have been wet. The vesicles are much larger. The color is also grayer. The red color here, I would say, came because of oxidation of the iron in it and would have occurred if there was an atmosphere. And so there are some indications to me that there was an atmosphere and ocean on Mars at 49 million years ago, but it was gone by 13 million years ago.
Yeah, you were down over on those lower pictures there. Yep.
This shows clearly to have been wet at one time because what it was, this was inside this, and it had to have settled into a sandy pool at some point. And so this is clear evidence that this rock was wet to me. I don't know if the moisture was local, something that had risen from from the volcano venting and made a little pool locally, or if it was ocean material. But again, look how small and how delicate the little walls are. This has not been moved much. If it's been in the water, it hasn't been moved enough to knock off these little tiny sharp edges.
Can you start that back over? These samples were taken. Just talk about where they were taken from on the meteorite itself. Okay, go ahead.
Okay.
Just tell, not show. Just tell.
Okay.
I'm doing the close-up. Just tell. Okay.
This sample came from the core sample out of one of these little pieces and was taken from one of the vesicles, the larger vesicles. The contents came out intact. I call it like a little clod. It was all held together by the particles.
Trying to follow your lower hand, it keeps dropping. We'll try again.
Okay. This sample was taken from the core sample. It came from one of the larger vesicles in the core sample and fell out intact. The bonds that was holding all of this together were the bonds that formed when the water evaporated from it at some point in its past. I added water back to it so I could see what it was inside and found this little rock inside. And clearly it has been wet at one point, but not wet very much. We can tell that it hasn't been in a lot of water because of all the sharp edges and angles on it that would have been broken off if it had been tumbled much in the water. And it was taken from, I believe, this very sample right here.
Okay, hold it real still so I can, I've got to move in 10x digital here. Now point to it.
You see the larger vesicles on
That works.
the core sample right there.
Okay.
And of course every vesicle in it was full of sand of some type, but it just fell out of most of them as a little pile. All of that I have in petri dishes and has been captured, and this shows how much sand came out when I took those core samples.
Point up to the petri dish. Okay. That's got it. Okay. It's a piece within a piece. Okay, go ahead, Mike.
This is a possible volcano of origin for the Frass meteorite. NASA also thinks it's a possible origin for several of the meteorites they have. What we have is one of the very large volcanoes on Mars. This would have been the ancient ocean shore that you can see around here, and so this part would have been in the ocean. This would have been a lake at some point, and this would have been a river contributing down into the ocean from the volcano. What we have here is a large asteroid impact that had come in from this angle and struck right here and ejected material out. One of the reasons that I think that the Frass meteorite could have come from here is because we see so many things that tie in with the Frass meteorite. First of all, we have apparently ocean sand in the meteorite. Well, this would have been all ocean sands right here. We have ocean creatures, which would make sense, but we also have land creatures that we find in the meteorite. They could have come from here or been washed downstream from up above. Also had the one flying insect that we found in the meteorite. And so everything about this appears to be a possible site. Also, each one of these appear to me to be side venting of this ancient Martian volcano. Some of this appears to have occurred after the asteroid impacted, and so this volcano may still be active on Mars. The last stage of my rock was made 13 million years ago, and in geologic terms that's not very long ago that this could have been active. So all of this ties together to have all the characteristics apparently necessary for the meteorite to come from this location.
I'm rolling. Okay.
All of the potassium argon testing was done at Geochron Laboratories by Dick Reisman. You can see that this sample came back at 12.9 million years, plus or minus 0.5 million years. That represents the gray material and is the predominant part of the Frass meteorite, probably 95% of it. The next.
Now I'm going.
Okay, for determining the ages of the Frass meteorite, I used potassium argon dating, which is the accepted method in the community. Geochron Laboratories did all of the age.
Just plain point to that age. Right, put your finger right underneath it. Okay.
Probably should have
In
cleaned my
fact,
fingernails.
just make that, put your finger under it, like, that's it, attaboy. Okay, good. Now, do the same thing very close up
And focused.
and focused, yeah.
You mean do that?
Alright.
Do the same thing again?
Well, you know what, I can even go in. The closer I get, the clearer it gets.
You can definitely read that, so we're in the right category, aren't we?
Now do that same thing with your fingers. Hold on. Million years. And now just say a sentence that would go with that.
And here we see the results was 12.9 million years, plus or minus 0.5 million years.
Results of what were they testing? Say it again in terms of the full sentence.
Okay, the potassium argon dating on this sample turned out to be 12.9 million years, plus or minus 0.5 million years. This would be the age of the gray material, the predominant material in the Frass meteorite.
Good. All right. Now, we'll go back up to geochron. And you can start that again.
Okay, I'd say that all of the, well, let me start over.
Yeah.
To determine the age of the Frass meteorite, I used potassium argon dating. I employed Geochron Laboratories to do the dating. Dick Reisman is the head of the laboratory and supervised all tests. We consulted on a weekly basis for quite a number of months as we went through this process. And we determined the ages of each of the different materials. The first age is the age of the gray material, which is 12.9 million years, plus or minus 5 million years.
Good. Go.
Ready? The next sample that we tested was a combination of the two rocks. It was composed of some gray rock and some red rock. It came back with a potassium argon dating of 27.9 million years, plus or minus 0.9 million years. This clearly acted as a control and showed that our testing was done properly, since the mixture was halfway between the two dates of the two different materials. Sample.
Oh, missed it. I wasn't on. Start again. Sorry.
The final sample is the red rock strictly by itself. I took over 2 weeks and carefully went through each particle, examined them under natural light to determine the color and the density of the rock, and picked them out and sent those in, and they came back with a potassium argon date of 49 million years, plus or minus 1.3 million years. You ready?
Okay, I'm going to start that again. I was just one zoom out. And I'm going to have you go ahead and go while right after I... Oh, I'm recording. What the heck? Okay. Go.
This last paper is a letter that I received from Dick Reisman at the end of the testing. He clearly says in here that the three ages are different in the meteorite. He also says that the potassium samples are about the same, which is what you'd expect scientifically. It's the argon content that varies over time. Potassium is about the same, since the material was all made from the same volcano and about the same spot. So he adds additional evidence in his report to me. As you can see in this paragraph, Dick Reisman clearly says you now have three quite different ages from this sample, ranging from about 13 million years to about 49 million years. About the only thing I can say about that is that this sample seems to be quite inhomogeneous in its radionic argon content, since the potassium content of the three sample aliquots are not all that different. This could well indicate that the sample does indeed have components of different ages. Yep. Some of the prime evidence comes from this boundary layer. This is the older red rock at 49 million years old. This is the younger rock at 13 million years old. This is all that separates the two of them. It appears to be a fine layer of dust, butterscotch colored. It appears that this is all that happened in the 36 million years between that lava flow and that lava flow. Everything about the meteorite indicates that this was all on the surface the entire time. So this is how much dust apparently was blown in 36 million years. The Texas Panhandle is dry, but it's not that dry.
Okay. Kind of want to try that again because I want to do it just a little differently.
Okay, start over again.
Yeah. Go ahead.
Some of the most important evidence of the Frass Meteorite Martian origin is this 36 million year boundary layer between the two ages of material. This is your 49 million year old material. This is your 13 million year old material separated by 36 million years of dust. Apparently this is all the dust that blew in, and by the way, it is butterscotch colored, just as the dust and sands on Mars are butterscotch colored. Apparently this was all that happened in that 36 million years.
Go ahead.
This picture here clearly shows the fusion crust, the melting that occurred when it came to the atmosphere. All through this section you can see a large plateau of melting. Here's another section of melting that clearly shows the sand melted, indicating to me that the sand was laid down and was on the meteorite before that it came through the atmosphere.
Okay, now go back up to the top, and I'm going to zoom in real. You can see how I'm getting close.
You can see this area of melting right along here. This was what stuck out the most on this part of the sample, and this little plateau is all all melted.
Okay, move down to the next one. Where we at?
Here's the next photograph.
I got to move in closer. Super close.
I can't even really see this either. It's,
I have to focus.
and it has glare in the picture, so.
Yeah, that's something I can't eliminate. That's okay.
Yeah.
Well, I'm going to show that it is a picture, so that's as close as we can get. Okay, go ahead.
Here's another area of clear fusion crust. I think the thing that's interesting about this photograph, though, is it shows the yellow fusion crust where the sand was actually melted, was on the meteorite, and when it came to the atmosphere, the sand was melted along with the rest of the rock, and in places you have yellow fusion crust to go along with purple, black, and other colors of fusion crust.
Go back and explain that was there's some glare on the picture, though, okay?
This is a picture I took with an inexpensive microscope and shows quite a bit of glare in the picture, but you can still clearly see the melting, the fusion crust that occurred in this region, even the places where the sand itself was melted and formed a yellow fusion crust.
Okay, next one below it. Did you talk about that?
Yes, this is the structure of the meteorite.
It's a super close up. Okay, go ahead.
This is the structure of the meteorite, showing the very thin, delicate walls and large vesicles that make up the entire rock. This is what gives it a structure similar to a space shuttle heat towel, allowing it to dissipate heat readily, as each of the thin walls do not carry the heat inward.
Okay, now did you want?
This is the magnetic particles.
Okay, go ahead. I'll follow your finger down slowly. I'm getting a crappy picture. What does that look like there?
Yeah, it's not very well in focus here
Bad
either.
as it is.
Yeah, it's not in focus itself, but I've still got the magnet with all the pieces on it. And I've got a much better. I've got pictures on the website too. From a distance, this one looks okay, but
go ahead with it.
what you're seeing here is the magnetic dust particles that came from inside the meteorite. This large area is all the magnet, and these are all the particles that stuck to it when I waved the magnet over the sand that came from the interior of the meteorite.
Move your finger in and out of it at each time.
Okay.
Now go ahead. That's one. That's two. I'm gonna try that one again. I have to go back. Okay. I'm recording this. I'm not running out of tape, by the way.
Well, I think we're about got it.
On camera, go.
Yeah. This section here represents just a represented sample of the contents of the Frass meteorite. You can clearly see that the vast majority of the particles are basalts, clearly from a volcano. Dr. Treeman says that we cannot use those samples because I labeled them sand. But I labeled them sand only because they were more sandy than the other parts of the meteorite, and everything that was tested was directly from the meteorite, and I believe clearly shows that everything in the meteorite is a basalt or a basalt derivative, and my tests are valid and should be considered. Samples and things from it. That's where sample 2 was taken. In those little yellow patches too.
Talk about the samples that you, talk about these samples that you have encapsulated. Go ahead, say something about them. As I zoom in.
Okay, we have a number of samples starting.
I'm going to start over with you. Go ahead.
Oh, I don't have a microphone on.
Oh, you don't.
Just hold it there.
Go.
We have a number of samples here, starting on the back row from left to right, is several pieces of the rock and the internal contents that have come out of it. In the front center, we have a piece of the core sample. On the left is a little colony of the glassy creatures and a bunch of other things that came out of the bottom side of the meteorite. And in this particular sample, I fed a fly to the little glassy creatures, and they appear to be eating them. And then over on the far right, in the front, we have a little colony of them. This is the original one. It's on my website. It's been growing. I've been documenting for 3 or 4 years now that it's been growing on a yearly basis. Not much closer. Here's the little colony right there.
And the others on the side?
Yeah, and this one here, what happened was I put water on it just to see what happened, and it turned into a silicone glue. It glued itself to the bottom of the petri dish, and it's been growing ever since then.
Go ahead.
Turn it.
Yeah, turn it. Sideways. Okay. Now back it off and talk about it while you're turning it. Do it.
This is one of the core samples removed from the interior of the rock. It's very delicate. It's also one of the pieces I've used to do the heat experiments on this far end to see how well the material could withstand heat. And here you can see where I took it to over 1,000 degrees, melted it, and then was able to hold it in my hand in 5 minutes. It was perfectly room temperature. The material dissipates heat very readily, much like the space shuttle heat tiles. I don't even remember this one. I don't know anything about it to say other than just a sample. Here's a sample of internal contents. This would in essence be the surface of Mars.
Go ahead and turn it. Talk about it.
Okay, now we're turning it over to look at the bottom. Right to the bottom, and one of the things we want to show is the particles that break off every time this just sits under Earth's gravity. The rock is so delicate, I heard it break then, the little thin wall sticking out cannot support the weight of it, and whenever it's set down in Earth's gravity, there's always a little pile of debris of little things broken off. Other things we're showing here, this is the 49 million year old material.
I was focusing on the debris down there. I was panning across. Okay, now I'm on it. See, you can see where I'm at. Start where you are. Okay, you can go ahead.
Okay, the redder colored material here is the older material. It's the 49 million year old material. It was on the bottom when it came to the atmosphere, and you see it suffered the worst damage. All of this has been melted almost into a slag type material. Here's places where I've taken samples trying to determine how deep this layer goes. I've taken samples here and here and other places. This is the location of the main core sample too that we took.
Okay, try that again. Point to the core sample.
Okay, here's the place where we took the core sample in this hole right here. This hole over here is a natural crevice, natural hole that was in the rock. Probably was full of sand when it first came to the atmosphere, and I suspect when this was coming to the atmosphere that sand was coming out all sides of it, every pore and crevice, and it was probably pretty spectacular.
Now go ahead and turn.
And we're turning the rock just to look at the different sides of it. Should be able to see the butterscotch colored sand as it sticks out in different places around the meteorite. There's clear streaking that occurred when it went through the atmosphere. Some of the red material, some of the gray material. You can see the boundary layer right here between the two. Here you can see some of the butterscotch colored sand and again the boundary layer between the two materials. See that it's very, very fine and delicate, very small. Another sample was taken here. More streaking, more melting, more of the old material here. More of the butterscotch colored sand. This would have been the nose of the meteorite. It's upside down when it came through the air. You can see the streaking that occurred. The vesicles would have been heated and elongated in the direction of the airflow, and that's what you see all over the meteorite.
Run your fingers over across the way the airflow will be going. Oops, no. Just that, the way you had it was good. Okay. Well, that's all right.
Now, right here is what I was trying to
All right,
show.
turn it so it shows. You can see in the camera what I can see.
Yeah, it's the air flowed across here. It looks like to me it kind of split right in this region.
All right. I was trying to get up really close and then have you rub your fingers over to show it. Try that on that angle. Can you see over there?
Yeah, it's hard though because I'm getting different directions. I'd like to turn it back right side up too and show the orientation of flight.
Sort of
Now,
a jerkulator shot.
I'm sorry. This would have been the orientation of flight. This would have been the nose. If you think of it like a space shuttle, this would have been the front where the pilot sat. This part here would have been the bottom, and you can see it received more heat. The top received less heat. These two things here acted kind of like wings. If you see from the top, we have kind of a triangle shape. This is where we get the lifting body effect. Also, there was a crevice under the bottom of it, which I think tended to help orient it in flight and keep it flying in a single orientation. So you would have had an airflow splitting and going down both of these sides. as it was flying through the Earth's atmosphere.
Go.
And you clearly see the melting in this area. It occurred all through here.
Yeah, I don't know where you were at.
Yeah, it showed.
You were in the shot. Try again.
Yeah, I was. Well, I saw it over there. This would have been the nose cone. You see the melting that occurred on the bottom edge of it.
Good. You're doing fine.
I've just got it balanced on one edge, and it's not doesn't set that way naturally.
Just thinking of doing some motion control stuff here.
Yeah, I'm going to the van.